Okay, please go ahead.
Thanks, Gary, for organizing this and for inviting us to speak here today. Welcome, everybody, to the Water Loss Specialist Group webinar series today. Today, I would like to talk to you about stainless steel service lines, a durable, fit and forget solution to water loss. My name is Nicole Kinsman. I'm a metallurgist and I work for the International Molybdenum Association. With me, my colleague is Benoit van Hecke from the Nickel Institute, and he's also online today. We have prepared this presentation together. Here is a quick overview of the content I would like to cover today. I will quickly talk about Team Stainless. We are organizing this webinar. Then about water loss. Where does it happen? We talk about the solution, stainless steel service lines. I will have a short installation video. I will talk about the benefits of stainless steel. I will give you two examples, Tokyo and Taipei, and then talk about the cost savings that have been achieved and some conclusions. So who is Team Stainless Water? Team Stainless is a group of associations. In particular, all related to stainless steels. There is ISSF, the International Stainless Steel Forum, which is the association of stainless steel producers worldwide. And then there are ICDA, the International Chromium Development Association, the Nickel Institute, IMOA, the International Molybdenum Association. And we formed together an alliance of organizations interested in stainless steel and in market development of stainless steel. So we're all nonprofit organizations demonstrating the benefits of stainless steel for water distribution. What is the role of Team Stainless Water in this context? We have come across this really interesting application of stainless steel several years ago in Tokyo, that they have replaced essentially all their service lines with Type 316 stainless steel, and they have found great benefits in reduced leakage and water loss and repair cases. We then found that also Taipei, Seoul, and a few dozen other cities in Asia have implemented the same solution. And so we thought, wow, this is a great application for stainless steel. We really should help to make this better known around the world. And so for that reason, we started on this project to promote the use and build awareness of the use of stainless steel in this application. We're not producers or vendors, so we don't sell anything. We are active in different parts of the world through our network in Southeast Asia, China, Australia, North America, and Europe. We encourage the building of local supply chains. This solution, the partially corrugated stainless steel service lines, are produced currently in Taiwan, in Korea, South Korea, and Japan. But if they are going to be successful, they will have to be also supplied or produced locally in different jurisdictions. So we're working with local suppliers on that. We also work on standardization. We have a standard now in China that we have been involved in writing. We have one in the United States, and we continue this as well. Then we support testing, for example, of course, things that go into drinking water need, for example, NSF approvals in the USA. We're working with the Water Research Center in the UK and similar organizations to to demonstrate that stainless steel service pipe are safe in drinking water. We also keep a small stock of tubes and fittings for trials, and we are supporting and documenting trial installations. So if this is something that might interest you for your utility, please talk to us about it. So let me get now into the meat of the presentation on water loss. Well, what is water loss? It's more than just spilled water. It's a waste of the precious water resource, of course, but also of all the work and energy that goes into water treatment, the waste of chemicals, also waste of electricity. The water-electricity nexus is a famous connection. Some 4% of global electricity go into water, supplying water. So if we think about this, we often say, well, we have 25% water loss, 30% water loss on average worldwide. It doesn't really tell the whole story, because if you need 100%, as you can see here on the right, if you need 100% water delivered to your customers and you have a water loss of 25 or 30%, you really have to start with 133 or 143%, and you have to have your whole production geared for 103 or 140 or maybe even more percent production to get at the end to 100% if you have these 25 or 30% water loss in between. So that's really something important and needs to be kept in mind. So if you're looking at this in practicality, if you need theoretically 3 of something, 3 tanks, 3 water treatment plants, 3 basins. If you have 25% water loss, you really need, in fact, 4 of those. To even theoretically only need 3, you need 4 to deliver 100% to everybody. So we have a good example here from Seoul. Seoul, as they reduced their water loss from over 25% to 2 or 3%, they were able to close 4 of their 10 water treatment plants. So this is not just the wasted water, but really the whole infrastructure that goes into delivering drinking water. Everything needs to be overdimensioned. Additional staff, infrastructure, maybe additional dams and reservoirs. And not just that, you also have high maintenance costs to detect and fix leaks. So you need more crews and equipment if you have high water loss. An example in Tokyo is that in 1979, before they started their big push to reduce water loss, they had nearly 70,000 leakage repair cases each year. So that comes to just under 200 per day. So imagine the crews that are necessary to fix 200 leaks per day. In 2019, 40 years later, after the implementation of their plan, of their replacement of all services and mains, they now have around 6,700 leakage repair cases per year, or 18 a day. So the whole setup is much, much smaller. It requires 90% less resources to detect and fix leaks in this situation. Should also say that the leak repair cases that remain are mostly on the customer side here, and related to mostly legacy materials. The actual leaks for stainless steels are very few, in something a couple of hundred, 200-300 per year is what I'm told. So this is these are leaks that are not belonging to the maybe private roads, etc., that are not belonging to the utility. So what are other repercussions of water loss? Of course, we have an increased environmental impact if we have to handle these 25, 30, 35% more water. It may be difficult to maintain water pressure. It could even lead to contamination of drinking water through soil ingress. And if you have leaks and flooding, there can be road cave-ins and collapse. There could be damage to buildings, all secondary effects. Not even to speak about traffic that is heavily impacted by works around this. And customers may not support water conservation if they see water loss in their utility. So that's another reason it's important to address leakage quickly. Now, another aspect is resilience. If you have a lot of water loss, you have lower resilience in the case of drought. And I tried to explain this here on this slide through a simple graphic. If we had a reservoir, and we have, let's assume here we have 25% water loss. So as we discussed, we need, of course, the 100% that we need to supply, plus the 33% that will be lost in the network. So in a normal year, we may have a 170 meter level in the reservoir, and everything's fine, even with 25% water loss. There is sufficient slack in the system, so to speak, that water can be delivered to everybody. However, in the case of a drought year, maybe the water level sinks to, let's say, 120 meter, just as an example. Now, your 133%, you cannot deliver 133% anymore if you have 25% water loss. You have a lack of water here, and it could lead to intermittent water supply, that you have to go to intermittent water supply. If you had, on the other hand, 15% water loss, that means you have to deliver 118%, 18% more than the theoretical need. You're just under the 120 meters here at 118 meters. So you are able to continuously deliver water, even in a drought situation. So just going from 25 to 15% water loss could make a big difference in the resilience. And we have seen an example in Taipei of exactly this. Taipei had a severe drought in 2002, but at the time they had a leakage rate of 28%. That meant that the levels in the reservoir went below the minimum that they could maintain or that they could work with. And so they had to resolve to intermittent water supply for 49 days in 2002. And that was a wake-up call for Taipei. And they started to look at what can they do to avoid such a situation. They are in an island, obviously, so there's not just piping in water from the mainland. That's not a solution. And so they looked at their leakage rate and said, we really need to do something about that. So in 2005, they started a 20-year program. And by 2014, they had an even more severe drought. They were down to 17% leakage, and they could continue operations throughout the drought and even had a surplus for a neighboring utility. So reducing water loss also means more resilience. And so that's a big benefit of not having as much leakage. So now I'd like to talk about where does it happen? Where does water loss happen? I think a lot of people I hear tell me that it's in the water main. The main is the big problem. But what we have found in a lot of cases, in fact, it's the service lines. It's not the water main where most water loss happens. And the service line between the main and the meter, and of course, also to some extent on the customer side, those service lines, they often have several connections, so maybe that's prone to leakage. The materials, may not be as sturdy, and it's also not easy to find the leaks in the service line because maybe they're smaller leaks, so it's not, they don't appear as readily as a water main break. But we find a lot of the leaks happen in the service line, and here is some supporting data from Tokyo and Taipei. Both utilities find that more than 95% of their repair cases are in service lines. So the mains are a very small, small part of the problem. If we now go to if we now also look at the impact of these leaks, this is a graphic that has been developed by Mackenzie and Lambert already nearly 20 years ago, and it talks about leaks and the runtime of leaks. So if you have a main leak, a reported water main break that may have a leakage rate of 75 or a gushing of 75 cubic meters a day, generally you become aware of it quickly, it's reported, and you fix it within a day. So the water lost from a water main break is relatively small at 83 cubic meters here in this example. Now they suggest that maybe a reported service connection break could have a much smaller leak, a much smaller water loss of maybe 25 cubic meters per day. But between awareness of that there is a leak, and then the finding of the leak, the localization, and then the repairing of the leak, several days may pass, maybe more than 2 weeks. So during that time, these 16 days that, we can say 20 days, we can say 10 days, but we say 16 days, it's about 400 cubic meter of water that's lost. So a lot more than in a water main break. But what about the unreported service connection breaks? Those that don't come to the surface, they may go on for months. So I gave an example here of maybe 6 months. That could be more than 4,500 cubic meter from a relatively small service connection. So another one that I have added here is the unreported service connection leaks that are considered unavoidable background leakage. These are the leaks that can't even be found through leakage detection, through normal leak detection. They are 10 to 20 liters per hour, so they're kind of under the detectable limit. And they also give you between 80 and 180 cubic meters of water loss per year. So these are, these add up. They are, everywhere. You don't know where they are. They're in all systems. And in fact, Taipei has said in some of their documentation that these type of leaks are really only, they cannot be found, they're not reported, so they can only be addressed by complete replacement of the system, by putting new service lines into the system. So just to visualize this, what I just mentioned, this little this little gray area here would be our water main break after 1 day. Here we have the reported service connection break, which may take 16 days to fix. And this is how much water is lost, graphically representing the volume, if you have a 6 months running service connection break. And here I put down these unavoidable background leakage for a year. If it's 15 liters an hour, this is how much comes out of the system. In 5 years, this much. In 10 years, this much. And who knows how many thousands there are in a system. So the water loss from services is most certainly higher than from mains, mostly due to the runtime. That's the big difference. So what we propose, what we found in Japan, in Tokyo, and in other parts of Asia is this solution, stainless steel service lines. So they connect the water main to the meter, and they represent a durable, cost-effective solution to leakage. So what they've done in Japan is to, instead of what usually is a straight tube in stainless steel, a rigid straight tube that has to be connected with fittings, elbows, T's, etc., they have created a partially corrugated tube that can be bent here manually to exactly how it needs to fit. So this is the development. It happened in the 90s in Tokyo and was implemented since 1998 there, and is really a very, very robust solution to service lines. I will start here a short video that explains a bit more about this.
Water utilities worldwide lose an estimated 30% of freshly treated drinking water through leaks in their distribution network. A stainless flexible service line made from stainless steel partially corrugated tubing is an effective solution for service line applications. Over the last 40 years, across millions of connections in Asia's largest cities, stainless steel service lines have been proven to dramatically reduce water loss and the number of repairs required. Stainless flexible service line is a robust, safe, and highly durable solution. It offers water utility companies and authorities major benefits. With the ground prepared, the installation takes less than 20 minutes. Its installation is quick and easy, with the added benefit of being totally flexible. It's easy to install, it's cost-effective, and above all, it offers an environmentally sustainable solution that will ensure the delivery of safe water supplies for generations to come.
So this system, as I just showed, it's easy to install. It consists of at the water main, it consists of a tapping valve and saddle. So it's a very strong saddle that gives a very good connection, and is even in earthquake situations very robust. There's very, very few times that in several tried and tested earthquake situations that any saddle would have come loose. So then there is a tapping valve coupling which connects to the stainless corrugated tube, and this connection is very strong as well. It's seismic resistant, earthquake resistant, and has been developed this way. And then on the meter side, we have a coupling similar to that one. So what are the advantages of this system? So we have fewer joints because we only have them at the meter and at the main. It's easier to install, as I just showed, and it's quick to fit with relatively little training. It's resilient, bendable, and flexible. That this flexibility is very important. It makes it resistant to earthquakes, soil movement, mechanical damage, traffic vibration, even mechanical damage. If a backhoe would by accident catch onto it, it will not easily leak or break or disconnect, it will be very robust. And the connections are really strong with very high slip-off force, because the stainless steel, we have 1 millimeter stainless steel tube here, is very strong, so it can a strong connection can be made with these compression type fittings. And now I'd like to have a very short video here that I'd like to show.
All steels are iron alloys. Adding chromium to iron creates stainless steel. Chromium atoms react with oxygen in the air to form a thin, invisible layer that protects the stainless steel. If the surface becomes damaged, this layer reforms, protecting the steel each time, keeping it both stainless and resistant to corrosion. This process is called self-passivation.
So self-passivation, that's the secret behind the corrosion resistance of stainless steels. A thin passive layer protects the stainless steel, and that passive layer really depends mostly on chromium, but also on other alloying elements such as molybdenum, etc. There are different stainless steels with different levels of corrosion resistance, and one that has quite a good level of corrosion resistance, particular for soil and water, is type 316 stainless steel. So it resists soil corrosion in these conditions. If the pH is bigger than 4, the chloride content of the soil is below 1,000 milligrams per kilogram. Conductivity is above 2,000 ohm centimeters. So in these conditions, stainless steel type 316 is found to be performing well. Also on the drinking water side, there is no problem for a wide range of pH. Chlorine up to 5 ppm continuously could theoretically be resisted. Also, chloride contents under 1,000 parts per million are fine for type 316 stainless steel. So for that reason, because it's corrosion resistant in soil and in drinking water, it's really a very robust solution for service pipe. This has also been tested in long-term soil corrosion tests in Japan. There was a big testing program in the 80s, or actually in the 70s, before they started to decide on which material to use for the service pipe. There were originally 25 test sites all over Japan, and many different materials. They were installed horizontally and vertically to different depths with different connections, and 1, 3, and 5 years. And after that time, they decided that they wanted to continue some of these tests, and they selected 10 test sites for a total of 10 years. The test showed that stainless steel had better corrosion resistance than some of the other materials that were tested. And type 316 here performed particularly well, better than type 304. Because some of the chloride and sulfate concentrations in the soils were quite high in some locations, particularly high, a material with particularly high corrosion resistance had to be selected. And as a result, Tokyo and also other cities chose type 316 stainless steel for the service pipe application. Now, stainless steel has more benefits than the corrosion resistance. It's also impermeable to chemicals, to hydrocarbons, to pesticides, etc. And it's safe for water and soil. It does not react with soil or water, and releases really minimal amounts of any alloying or of any elements into either of them. So it's it's safe for water and soil. It's practically inert. It's also resistant to extreme heat and extreme cold. Even a fire situation, like a wildfire situation with a buried stainless steel will not affect it. It will certainly not melt, and water will not be contaminated through any ingress through the stainless steel. It also has very good toughness, really fantastic toughness and ductility down to very low temperatures. It's used in cryogenic services, so much lower temperatures than we will ever encounter in nature. And there is no cracking or bursting due to maybe frozen water in the pipe. So stainless steel contributes to resilience in extreme events. It's also hygienic, maybe that's obvious. Pharmaceutical production uses copious amounts of stainless steel. Operating rooms in hospitals, clean rooms, dairy plants, food and beverage production, commercial kitchens, water treatment plants. So stainless steels are already widely used in many hygienic applications. Then stainless steel is also sustainable. It's 100% recyclable to original quality, and that's done every day all over the world. A huge amount of stainless steel, the vast majority of stainless steel at its end of life is collected because it's valuable and is recycled into new stainless steel. There is no environmental impact during use. It's durable with very long service life. We have some applications that are as old as stainless steel itself, or nearly as old as stainless steel itself, such as, for example, the Chrysler building in New York is still from the 1920s, and is still doing well. There is no applying or reapplying of any coatings necessary because it's corrosion resistant. And overall, we can say it saves water, energy, and CO2 emissions. So let's now look at the examples that I have mentioned already. The first one is Tokyo Bureau of Waterworks that really originally started this use of type 316 stainless steel. It's a huge utility. They have 2.2 million connections, service connections, nearly 14 million inhabitants, some 1.54 billion cubic meters of water distributed per year, and 27,000 kilometers of distribution pipe. What's really important is that it's prone to earthquakes, so has regular earthquake events. And in the late 70s, the leakage rate already wasn't so bad at 15, 16, 17%, but they were growing strongly in Tokyo. The city was growing, and they were worried that they wouldn't have enough water for everybody. So they started to look where to save, and leakage was one of the solutions. So they came up with a program that does not only, it wasn't only the replace, but they replaced all services and mains. So that was over 25 years or so. You can see here how they have replaced all service lines with stainless steel, and they arrived at 100% here around 2003 or 4. Also, the mains have been replaced with ductile iron mains, and many of them seismic resistant ductile iron mains. And so in addition to replacing all service mains, of course, they also divided the city into DMAs. They did increased leakage detection, in faster leakage repair. And all of these measures, they have led to this reduced leakage from 15.5% originally to about 3.6% right now. And they're holding around this 3 to 4% for over 10 years now in Tokyo. It's also what's very important also for cost savings are the number of leakage repairs, and they went from some 70,000 to around 7,000 per year, as I mentioned previously. So if we're looking at the installation of stainless steel service pipe, we can see that 90% of services are now over 20 years old, and 60% are over 30 years old. So it's not that all of them have been installed yesterday. And all of this leads the city to several hundreds of millions of US dollars of savings per year, both in avoided water loss and in reduced repair cases compared to the original 40 years ago. Now, we have another example, Taipei water. They started later. I mentioned the impetus there was that drought in 2002. Taipei is smaller, has 300,000 service connections, a population about 4 million, and about 824 million cubic meters per year. They have 6,300 kilometers of mains and services, and they're also prone to earthquakes. So they're only maybe 40 or 50% into their replacement project, but they start in 2005, and they already see a significant reduction in the leakage rate from around 27% in 2005 to about 12.7% in 2019. Their yearly repair cases have also dropped from 10 to 12,000 to just over 2,000. So that's also a cost savings. And really probably most important to Taipei is that they had no service interruption despite the drought in 2014. Taipei they also did all the other things as well. It's not just the stainless steel service lines and the mains replacements. They also did divide the city in DMAs, and they tackled first the highest leakage rate areas. They have better leakage detection and also faster leakage repair. So now I come to the cost savings and trying to quantify this is not easy, but really the cost savings are the water that's saved, that's not lost, and the reduced number of repair cases. At least that's how both Tokyo and Seoul calculate their net savings. And again, it's not easy because these are projects that go over really decades, and to kind of figure all this out, it's not so simple. But what I've seen, Tokyo has reported that they think they have net savings of about $3.5 billion of this whole project. And that comes, these are the exchange rates just from this month. They divided up like this. The investments were about 2.3 billion, and the savings due to reduced leakage and reduced repair cases was $5.8 billion. That was reported in a conference, in a Q&A at a conference in 2018 at the Tokyo IWA, at the big Tokyo IWA annual conference. Now, Seoul has some data on its website, and their net savings are about $2.3 billion by 2013. So this is how they reported it between 1990 and 2013. Overall, they invested about $3.1 billion for the replacement of their pipelines, both services and mains, and the savings are about 5.4 billion. And here is how they they calculated that. So a net saving of about $2.3 billion. Seoul also has very similar reduction in leakage cases to Tokyo. They started at similar numbers and have reduced them similarly. Yeah, so that's the really positive story that that these cities have been able to generate, in addition to better resilience, etc. So to come to the conclusions, most leakage cases are in service lines, and type 316 stainless steel has excellent resistance to corrosion in a wide range of soils, but also in water. The corrugated stainless steel service pipe stops leaks, and it's hygienic, it's strong, it's corrosion resistant, seismic resistant, fire resistant. It can yield to massive cost and energy savings, and it reduces the maintenance and improves resilience. So with this, I'd like to thank you for attending the webinar today. I also would like to, contact us for questions you may have. And also, if you're interested in maybe a trial installation at your utility, please contact us, either Benoit or me, and we'll be happy to look into that and possibly help with this. There's also, we've just published a small brochure that you can see on the right, which is available from the teamstainless.org website. Thanks, that's concluding my presentation. So are there any questions?
Nicole, maybe I can start reading the ones from the chat. The first question that I come across here is the tube diameter. So I think that the most commonly used stainless steel partially corrugated tube has a diameter of 20 millimeters, or that order of magnitude. Would you say that's correct? Yeah,
that's correct. 20 and 25 I think mostly it's 20 millimeters. 25 is another common size.
Okay, thank you. There is a question about how does the energy consumption for recycling compare to aluminum?
Well, I don't have this information with me. I don't know if Benoit, if you have any.
Yeah, we may have to come back to that one, but maybe highlight that in this context, which is partially corrugated stainless steel tube for distribution pipe, that aluminium is not really in the picture, regardless of how the material compares to stainless steel with regard to recycling. So I believe we would be happy to come back on the matter, but we don't see it as very relevant against the background of this specific subject.
Yes.
Okay. Then I have one about corrugated stainless pipe. Is it difficult to produce? Now, we didn't show a video about production, I think, but the product is being fabricated at industrial level, and stainless steel is particularly suited for that, especially nickel-bearing stainless steel, which nickel content offers advantages such as ductility and formability, and in that sense makes it particularly well suited to transform the straight tube into corrugated tube. So I would say no, it's not difficult to produce.
Yeah, it requires the adapt machinery. It's the process that is used is hydroforming, and it
Yes.
is yeah, it's just the machinery needs to be in place, but it's not difficult.
The next question is about the existence of any specification for the partially corrugated tubes. Maybe Nicole, you can shed some light on what's been accomplished in the ASTM.
Yeah, so I mean, there are specifications. There are the original one from Japan. There is one in Korea and one in Taiwan. We now have one in China, and we also have an ASTM specification. I don't have the number of it, but it was just maybe 3 or 4 months ago. It was actually, it has become an official ASTM specification also. These are the ones I'm aware of.
Okay, thank you. So it's certainly not a barren landscape there. Various areas of the world offer adequate support in terms of standardization. I have a next question, which asks about how the tubing connects to the corporation stop and the meter. Now, I think, Nicole, that both the video and the images showed the type of dedicated fittings that can be used for that. And I'd like to point out, if he is with us, that we have a Mr. Kim Burton on the call, who is the most qualified specialist to address those matters. So don't hesitate to be in touch with Kim here. But any other comments?
Yeah, I mean, I think we would. Yeah, I would say that it's typically, or how they do it in Asia, in these cities that I mentioned, they don't use a corporation stop. They use this saddle, and you can hot tap into the saddle. It's made that way, which gives just a much stronger connection than just drilling directly into a pipe. So that's how because they need the seismic resistance in Tokyo and in Taiwan, they've done it that way. And these connections, we could maybe share some pictures with you, Larry, so you can see exactly how they look. These are very strong connections that are also seismic resistant, that are kind of compression type fittings. They are called sleeve-in fittings. They give a very strong connection to the tube. They almost kind of dig into the tube a little bit. There's some they squeeze onto the tube and indent it slightly to make a very strong connection.
Okay, thank you, Nicole. I've arrived at a question from Luis about the thickness of the tube.
Yeah, generally it depends on the size. And I mean, we did say 20-25 millimeters is the most common. It exists, in fact, from 15 to 50 millimeters in most standards.
That's the diameter, Nicole.
That's the diameter, exactly. But just so it depends on the diameter, what the thickness is of the tube. Mm-hmm. And the most common, the 20 millimeter, has 1 millimeter tube thickness.
Okay. Mm-hmm. The question from Jomar, is it possible to produce larger diameter of partially corrugated tube, for instance, to be used on secondary or tertiary lines?
Yeah, yes, it is. In fact, these kind of tubes are also, or pipes are used in chemical processing plant, etc. So it's definitely also in Taipei and in Tokyo, they are using these larger diameter pipes like that, partially corrugated, for certain applications, in particular where they have difficult, strange kind of connections from, the geometry is not straightforward. They use larger diameter pipes for that. So it's done, yeah. That
brings us to a question by Eelco about the costs of this system and how it compares to PE pipes, which are very commonly used as connection pipes in the Netherlands?
Yeah, I mean, definitely it's just that the tube itself is a lot more expensive than PE, and I don't have a particular multiple there. But I would like to make you aware, and that's what they told us in Tokyo, is that the big cost in any of these situations is digging the hole. And if something costs even several times more, but then lasts for a very long time and it doesn't require again to be dug up, that's more important. So in Tokyo, I think the cost of the material was in the order of 10, maybe 15% of the total installation. And it would be a lot less if it was PE, but then the installation would have maybe had to be done more frequently again.
Yeah.
So I don't know, Benoit, if you have a better answer regarding exact costs.
No, there are no good or bad answers. What I would like to underline here is the way that these success stories are being fed to us as examples of how nickel-bearing stainless steel is the best material choice over the whole life of the installation. So I think, Nicole, you highlighted that in the presentation that some of those pipes are well over 30 years in the ground now with excellent service records. So it's the stainless steel that makes the solution affordable and even successful on the long run, and that's the right thing to do in a sustainability context, I think.
Yeah.
I see that we have a question. Okay, how is it compared to other plastic pipes? I think the financial question was discussed before. Mordecai, I'm not sure how compared should be read here.
Well, I mean, if you're looking at the life, I think I pointed a few things out. It doesn't, nothing leaches through it. It doesn't, it's not affected by UV light or chemicals or cold or hot. So it's much more robust, I would say, than plastic pipes. But yes, the costs are higher. There's also, Benoit, but just above, is there a standard length that these corrugated pipes come in? Can they be shortened? Yes, so they are currently produced in a standard length of 4 meters, which is sufficient for these, the vast majority of the cases that in Tokyo, Taipei, and Seoul. And they can be shortened with a regular cutter, with a regular tube cutter. That kind of.
Nicole has disappeared.
I have disappeared.
I can still hear.
Oh, good. All right.
Okay. You were eclipsed there for.
Oh, okay. So 4 meter lengths, and it can be cut by a regular with a regular tube cutter that's used also, for example, in copper.
It does have stainless steel wheels for cutting the stainless steel, Nicole.
Yeah, to make sure there is no contamination on the cut edge. Yeah.
Okay, so the question by Antutuko is again about the capital investment cost compared to plastic installations. I think Nicole gave a very accurate answer before about the 10 to 15% of the installation. Further than that, there is the interesting life cycle that stainless steel systems exhibit, and the fact that the major cost is with the breakup of the road. So it's not a one-dimensional question. The question from Romalin about whether the tubing is still good when it soaks in salt water. where Romalin is located, there are areas with low water tables and thus pipes that are most likely to be soaked in salt water. I think
so
sorry,
that would, that would be probably not advisable. I mean, it may depend on the exact content, but if it's over 1,000 parts per million, which it sounds like, if it's brackish water, and for long periods of, if it happens briefly, and washed off would be fine. But if it would be for long times, I wouldn't advise this grade of stainless steel. You would have to go to a higher grade of stainless steel that then is maybe less commercially available at the moment.
Yeah, but which we can still advise about.
Of course.
Okay.
Yeah.
Okay, the question by Sher Singh on how much to budget for materials to replace 1,000 service connections. That's a question I think we would love to be able to answer, but that probably would lead us too far right now. But it's definitely an interesting question here.
Yeah, maybe we can calculate it. And it's interesting, or probably people know that when you buy 10 or 20 tubes, as the organization, the Team Stainless are currently doing, the pricing that you get from a vendor is very different from somebody purchasing 10,000 tubes. So it's not so easy to answer, but we could try.
Thank you, Nicole. There is a question in two parts from Rio Hattori. Since stainless steel flexible tubing is so efficient, what is the reason people are not using this system? Is it because of the initial investment cost? Well, that is a question that, especially in this circle of specialists, can easily be reversed. We'd like to know. If you look at the size and the significance of the world cities that have embraced it, tested it, installed it since 4 decades now, there are good arguments in favor of it. Taking this success to different parts of the world probably hits obstacles such as habits, traditions, plumbing crews being familiarized with one material, not the other. It's definitely not a plug and play transition, but we believe it can be done, provided there is sufficient attention and willingness to learn something new material-wise.
Yeah, I mean, the current producers are relatively small producers that produce in a particular country, and they're not, big enough companies that they would just start to go all over the world and supply the material everywhere. So that's another hindrance at the moment, I would say, is that it's the availability it needs to be ensured everywhere locally.
Okay, we have another question about geometry and lengths from Arvin. Won't using standard lengths be difficult given different houses and buildings need pipes that bend and straighten at different areas? Well, I think we can refer to the installation videos here. Nicole, first of all, the pipes do lend themselves to bending and adapting at specific lengths. So I have not come across users pointing at that problem as a showstopper. But I don't know how you read this.
No, I think that's right. I mean, longer lengths are maybe if maybe in the United States, maybe also Australia, other places, they have more than 4 meter service lines. They might be longer. In Japan, they use connections between, so couplings between, if they needed ever longer tubes. We are thinking it would probably make sense to do an orbital welding in the production already to supply in areas where longer tubes are needed, to supply them longer, and then they can be cut to length as other materials.
Okay. I then have a question by Stephen about contact between galvanically dissimilar metals. If connected to, for instance, brass water meters, how can you overcome the problem of corrosion between dissimilar metals?
Yeah, so there are ways to insulate the two materials from each other. Within the coupling, there are couplings that are made for that. That's one way. In fact, on the water meter side, it's not such a big problem because the water meter doesn't sit in an electrolyte. Of course, there is one on the inside of the tube, but it seems that's not caused big problems if it's not buried. So in a water meter box, the brass meter typically also has much higher, well, not typically, is much more surface area than the tube. And so it, in the galvanic situation, it would be the brass that would be preferentially corroding, but because it's a large it's a large area, it's going to be less likely than if it was a smaller part of the connection. So it seems in practice that's actually what's happening mostly in Tokyo now, that the water meter is brass. We also, I think we saw a valve in the video that's a brass or a bronze. It's, however, I should say that also they have found that at the main side, that valve should really be stainless steel on the water main where it's buried, because there seem to be some problems when it's not the same material. Yeah,
which is why it's also available.
Yeah.
We have a question of economical nature. Do you have a report or statistics of market potential of a large geographical country like India in terms of market size or volume if they go for replacement of an existing system? This is a question we may have to take offline. But
we don't
if you look at the size, of what has been accomplished in cities such as Tokyo, Taipei, and Seoul, we should certainly be capable of deriving some metrics from that to engage in a discussion there.
Yeah, what's important is to know, I mean, that usually they know, a waterworks knows the number of service connections and the average length of a service connection. And then you can kind of multiply it with the material that's needed for that.
Okay, I think that brought us to the end of the questions for now. Of course, Gary Wyatt has our contact details, and we would be happy to provide more info, highlight all or some of the presentations to you if necessary. And also from my side, thanks for lending your ears to these presentations and for the interesting questions. Thank you.
Thank you.
Thank you, Benoit. Thank you, Nicole. That was an excellent presentation, and we had quite a few interesting questions as well. So thank you, everybody, for joining us. And we have one more webinar in 2 weeks' time, I believe. So keep watching for our announcements. Okay, thanks, everyone. Bye.
Thanks. Bye-bye.